Hello, my name is Luis Salgueiro. In today lab exercise, we will cover autographs and in PyTorch. Let me show the graph. So we will cover some basic operations like in PyTorch, and also we will explore the central package autograph that is really necessary for deep learning algorithm, that it provides us the automatic differentiation for all the tensors, and it's doing by run, so it depends on how you code, and in each iteration is changing all the differentiation and all the operators for these tensors. So let's compute, let's see how it's work, and let's also define some dynamic computational graph. Let's see the concept and how it's work, this dot backward method that is really useful for defining the operations in deep learning. Let's start by importing all the packages necessary to run this exercise. So let's import Torch. Let's also import Torch.nm, the API for the neural network layers and the operations, that also have available the Torch.optim for the optimizers available in PyTorch. Let's import as well NumPy. Matplotlib is a common matplot package for in Python. And let's start. So as this statement said, long short story, we will use the Torch.tensor to define some tensors and to define this graph. This is an acyclic graph, right? And in this exercise, we will use two tensor. We will multiply two tensors and to store in another tensor C, right? Let's see how we can build and define this dynamic computational graph, right? So let's start by defining Torch.tensor of 1, right? And the y, for the y will be Torch.tensor, right? And multiply this tensor and print the tensor C. So we can see that's already defined the multiplication, so it's all working good. And as we already saw in the previous exercise, that the tensors had a lot of attributes that we can use, and also we can explore a little bit more all the properties that already have defined the tensor. Let's define first a helper function, like we can describe tensor, right? And we can just well, let's explore x and the name of this tensor, right? Just to see a little bit more with the properties of available for this tensor. Let's here a little bit of factor to print here the name tensor, the name, right? And let's define also another description, the data, which should be x.data. So they're also available. We already see that required grad is another attribute that is available for computing for tracking all the operations, all the definitions of the derivatives. So we can explore a little bit more, like the attributes grad function that are also available here. Let's see how it's work. Right? Let's define also another description, like requires grad. Let's start requires grad, and bring as well the gradients for the tensor will be grad. Just dot grad this attribute, and we can print all as well the grad function that are related to these gradients. So grad function, and it also could be another. Yeah, seems okay. Let's just close this one. Okay, let's describe a little bit more the tensors that we already defined. Yeah, let's see that the name of these tensors and the tensor x that has a tensor of data with value 1. Wow, just a scalar. We didn't set already the requires grad attribute, so none of the gradient, and also didn't store a function related to the gradients. Explore the other tensors and describe as well for the y and for the sequence. Okay, we have already seen here that all this tensor had just printed all the values. That's it. All right. Well, perfect. So let's play a little bit more with the tensor. Let's define again the torch dot tensor, right? And let's see that if we define only the data, we can define the data type, the device that it should be. The device should be when we place the values to a GPU, for instance. We will explore this function later, and the required grad. Yeah, define the required grad to. In this, we indicated if we set this to true, we are indicated just to to PyTorch that all the to start the tracking of the functions and also all the derivatives from this occasion, right? In this occasion, we are requires what set to true for this tensor, and it will start tracking all the operations and also the functions depending on this tensor, right? Just for floating values here. Okay, let's describe again these tensors. We can just copy this cell and paste a little bit more here. Well, we have seen that it changed a little bit. For the tensor Z, it's starting to tracking all the operations that it should that this is a result of a multiplication between variables and starting to track the required gradients for this tensor. So in these occasions, there are nothing calculated yet, not a gradient, not a function for this tensor. So it's okay. So just starting to realize that it should be track all the operations and so on, right? So how we can calculate these derivatives just by tracking with this function, the backward function. Let's see that in the help of the documentation that it will compute the gradients related to the graph that we have defined, right? So there is a lot of there are others attributes here. We can set the gradient, return graph, and let's create a graph. Let's explore later these functionalities. We can press say z.work backward, and let's grab again these functions. Yeah, let's press here. Well, we can see that now we have a gradient here, right? A tensor with value of 2. That is a result, that's the gradient of this operation. Now, and anytime that you call a dot backward, it will calculate these gradients depending on the graph, right? And we can see here how it's work in this description graph. And we can see that anytime that you call a dot backward, it's another node is added to this graph. So in this node, it store the function that are resulting from this multiplication function, right? And for scalar, it's automatically added a scalar tensor dot one that in this case indicates that the chain rule is the last, it's the ending of the chain rule. So it just from this function is can compute the partial derivative in this occasion and store the value to the dot grad attribute to the tensor, right? So it's really easy, it's really smooth to work with to calculate the derivatives that are coming from different kind type of function operations, right? So, and also you can see that the graph function is a reference to the multiplication backward, right? So you can see here. Yeah. So far it's not too hard uh, to initialize these functionalities and this toy example. As we mentioned already, the C backward torch that tensor for one is automatically added to is by default, but in the case of an n-dimensional array, you should express explicitly the end of the chain rule, right? So it should be the same. It's the same dimensionality as the tensor C itself. Let's see how it's work. So on this occasion, yes, yeah, we can just erase these cells that we didn't use. Let's define again. Let's see the torch that once we can define as well. We can require graph set as true, and also we can define 2.0 for torch that let's see z should be result of this work. Yeah, okay. Let's describe the tensor x and pass the name of this tensor, and let's describe also the tensor c and just pass the name as well. Just to see how it works, right? So we can see that the results is a one-dimensional with three values. The values are 2, and the values in this case for the x tensor it's 1, right? Great, great. So it's the required grad I already set to true, but not a gradient is already calculated. So let's calculate the zero backward. And this we already know that we should express the gradients for n-dimensional array, the n gradient of the chain rule by default. In the case of an n-dimensional array, it should be explicit. So by just around this cell that it should provide us an error. Grads can be explicitly created only for the scalar outputs. Already we can already see. Notice that once we express the and it should be on the same shape as C, right? So it should be that once with the shape of C. And we can also remember, if you remember the first lecture, once like, and also just like pressing C, it should work. And let's describe tensor in the case of X. Right. We have we see that also works. This obtaining the gradients. That's a tensor of a one-dimensional tensor with three values, all by two, right? The result of a partial derivative of this graph, this computational dynamic graph, and it's also working. So far so good. And let's copy this cell by here. And one thing that I forgot to mention that these gradients are stored in the dot gradient attribute, and it's accumulated. Means that it's summed up every time that it has a gradient. It's called a backward, and if there is a backward, it sum up to that value, right? Let's call it here. Let's see. Yeah, we can show this operation. Let's call the backward operation again. And in this occasion, yeah, I will throw an error, right? This is not a problem because we are trying to show how it's work this retain graph operation, this retain graph attribute, and it should be anytime that you are calling that dot backward, all the graph it's already it computes the derivative, right? And all the graph is already gone by that time that it computes. So in this occasion, uh, you should indicate that Python should retain the graph for few further operations in the case that is needed, all right? So in this occasion, we can just represent here. Oh, as we already see, it's not defining already the graph, so we should define again. So x, let's describe again this tensor x. Oops, so it's not uppercase A, it's just lowercase. Yeah, we can see that it's having the gradients already. let's also define the graph again on this occasion. Yeah, we can see that it's already defined, and let's retain again the graph for further backward operations, right? So we can see that now for the x tensor, the gradients also increase, and now it's a change, right? So it's in the case of perfect, so it's accumulated. In the first operations, it's only a one-dimensional array with values of 2, and now it's a one-dimensional array with values of 6. So it's all dependent on the dot backward and the times that we accumulate. Any time that we call the backward, it can compute the partial derivatives, so it's added to the attribute in the dot graph of this test, right? So you can see here, that's what. Uh, so let's build our first neural network, and let's try a little bit. So in this occasion, we don't, we will use the NN package of PyTorch that all the neural layers all are already predefined. So let's import again, just to see, just for you to see how we can build a neural network. So for building a neural network, you should define a class. For instance, my net, we will call it my net, right? And we will import, we will inherit all the modules that are available for this class in this package, right? The dot module. For any neural network that we defined, you should define two functions: the init function, right? And oops, the init function, and also the forward function. Forward function. So for each function, in the init part are defined the constructor of all the layers. That it in the function, in the forward part of this, on the function forward, that we are connecting all the layers that we are defining in the init part, right? So we let's here by defining the self, right? And also we make a super class that just uh, generating all the initialization methods that are available in this an end module, right? Here, yeah. So, right. And let's call we can define our first multi-layer percentrum LP, right? So multi-layer percentrum has fully connected layers, right? Fully connected one should be a linear. Linear is our first operator, and it applies a linear transformation in this type of operation, right? It's like a combination of all neurons and a weighted sums, and also a bias here. Great. The attributes, the input variables are the in future. Let's start by 3, and the out future, let's say 20. Okay. Let's call the activation for this layer could be an H applied an element wise. So you can see that well, is a well common known activation layer. So it's not necessary to use to define any input variable to that layer. Let's define again another fully connected layer, but also be a linear, right? So in this occasion, we will receive the as an input variable the amount of the the output variable of the first layer. And let's define again a three. Yeah, just those three. That's okay. And let's define how are these layers in the init part function are defined, right? So we can call a variable let's call h1, like for the self dot f of we should also define the self and some input variable like x, right? And this x should pass as an input variable of the first layer, right? And then this output layer should be output hidden layer should be like passed from the to the activation layer, right? So we have already had this first hidden layer h1, and let's call the output of this neural network by just connecting the fully connected 2 that should receive this h1, right? The h1, the hidden one layer, and let's return this output layer, right? Great. So we have already defined this the first neural network. Great. So we can instantiate this class. Let's find our first instance, so our first object here, and it's printed how it works, right? We can see that our net is composed by a fully connected layer and an activation, and then a fully connected two. All the bias are set to 2, and this is the configuration, this is architecture of the layer, right? We can import, yeah, let's import another library, torch.summary. It's really important, import from, yeah, we can import from this torch.summary, import summary. Is a really is a this is developed by the community, and it's on developing, so it's really useful to explore. Let's see another properties of this network, and in this network we should pass to the summary. We can pass the instance of the network in, and you should also is passed as an input variable and some the input configuration of the layers, right? We can see that is how it's connected. It also uh, show us the numbers of parameters that are calculated total trainable parameters, right? And also, well, in this occasion, it's a really tiny neural network, but it's really useful to see all the connections between the layers. And in the equation that we have a key combination that you will see later on in another lectures, all the amount of memory that is required for storing these layers. So it's really useful. There are a lot of thing that you can explore with this library torch.summary. All right, we can also describe, let's explore a little bit more with the functionalities that has these are layers. Oh, the first one is the activation. It's a tanh, right? So let's let's spare another layer, fully connected one, and let's explore a little bit more. Yeah, let's have the bias here. We can see that it's a tensor. What is the shape of this tensor? So we can see that for each neuron that we have, for each output neuron, we have 20 neurons, right? So it's a one-dimensional array with one-dimensional tensor and with 20 values. It's the same. We can explore the weights, right? The weights from this fully connected layer, and we can see that is a one-dimensional array, two-dimensional tensor by with 20 rows and 3 columns. Let's describe this tensor. Right? We already have defined this tensor describe tensor function. So we should provide the tensor, right? So the name of will be fully connected one weights. Yeah, we obtained the name in the tensor. These are the values that are already pre-initialized. So random values. You can see that requires graph is already defined as true because it's how any time that you instantiate a class from a neural network, is all the layers are define the requires graph to true. They are ready for the backward operations. So, but not any gradients and any functions already defined yet. Okay. Can another thing that we can explore? Yeah, well, let's train this neural network. For training, we should define two more things, like the loss, right? Loss function. And in this occasion, we can use the dot. We can explore a little bit more the NN package. Alright. Oh, we can see that there are binary cross entropy losses. So there are a lot of losses that we can explore here. We can define the mean square error loss. Let's define here the mean square error loss. Let's use this one. And we should also, yeah, let's explore the optimizers that are available. There are the ADAM, the stochastic gradient descent, RMS probe. So there are a lot of functionalities here. And if we can see also for the stochastic gradient descent, there are parameters and learning rate. So we can see that there are a lot of possibilities here. There is also an example here. So we should express the net dot parameters for this optimizer, and let's also define in this occasion the learning rate, right? So let's first, what we can see here. Well, let's express a little bit more these net dot parameters, and the net dot parameters it will I will provide a list net dot parameters, and for p in params, let's print these parameters. Yeah, we can see that it's returned as the tensor, that this tensor, the first tensor requires grad, this second tensor should be the bias, that also requires grad. This tensor now, the second tensor for the second linear operator, that also requires grad. So this should describe also the first values for uh, this initialized neural network, right? That's already passed as a input argument to the stochastic gradient descent. So what else we should define? Yeah, it's already okay. We can try now. We can train our tiny little neural network. Let's define a function for training. Let's train, and this function for training should receive the network, the loss function, and also the optimizer, right? And also let's put the argument a number of iterations for training this network. Well, let's train like let's train here. Let's train a little network, a neural network that should map from a uniform tensor with random values from samples from a uniform distribution to a tensor from zeros. So it will map this, and we will track the loss values as well, and should plot it. That is a really good exercise to do. First, let's define our input value, right? Torch that torch should be run, right? And let's provide 10 samples anytime, and our as columns it should be 3, right? Let's pass this vector to our network, right? And let's calculate. Oh, let's define first this loss history and NT should define this first here, and NT list. Then what else? We have we can calculate the loss coming from this loss function. That should be the difference between the output layer and the torch dot zeros, like right from the output, right? It should be at zeros, right? We also perfect. We have our loss here. Yeah, we should track the loss by appending to this loss history. So the loss is a tensor. We should recover only the item from this tensor. And what else we can do? Oh, we should print, right? Let's print that if the number of iterations are divided by some any kind that any 50 times, it will just yeah, it will just print this value, right? Just print this value and loss. Right? What else? Let's plot. Yeah, should be plot. Utility dot plot, right? Is loss of the item. This loss function. And this loss function we can plot this time or not. Yeah, we can plot this time. Yeah, something's missing. Oh, yes, I remember. And define the train should be defined anytime for be in range should be the number of iterations. Okay? Let's call number of iteration. So anytime here we are calculating these values. So the loss, and we can paste. Oh, it's not necessary to find this inside. Perfect. So it's fine. Okay. Yeah, let's print this loss history. Yeah. And also let's print some labels or input our loss. This is the number of iterations, right? And it's already defined, also define the loss rate. So far so good. What's oh, we didn't use the optimizer. So anytime that the optimizer should provide unsteadiness. Also to perform unstep of this stochastic gradient descent. Sorry, pronunciation. So input tensor is here, so the network is here, calculating the loss, it's appending the loss, the optimizer is already, yeah, anytime iteration it will perform one step for the stochastic gradient descent, and then it will print any 50 iterations, the loss, then it will plot the results. Define house. Yes, okay. Oh, loss history, expected engine. So great. So perfect. Let's train our neural network. Let's pass the network. Let's pass these functions. Oh, let's call it different, right? Just two. We can go differently. Not to get confused. Right? So we can pass here the loss MSE. We can also pass the optimizer, and let's print it for, let's train it for 500 iterations. Great. Oh, you can see that now. Yeah, anytime. So it's not working to print it this way. Let's print it a little more. It's working a little bit more with our helper function. So any 50 operations, right? So it's printing here. So what's the problem? The problem here that we didn't, that the first thing to do is to zero the gradients, right? So the optimizer, two things are missing here. So the optimizer dot zero. Yeah, we should optimizer should be optimizer, right? Optimizer dot, which we should first zero. Yeah, we should, all the gradients should be zero anytime sure that its operation is started. And not remember, because we are adding the gradients anytime to the dot attribute of each tensor. So we should, all the gradients are zero, should be zero at the first moment that we are calculating uh, the back propagation. So also uh, we should back propagation. So we should use the backward operator to the loss. All the loss are this tensor here, and also are containing the errors of the functions here, right? The errors from the output and the dot and the zeros tensor. So the dot backward should return the gradients for all the tensors, and the optimizers will take these gradients and perform an stochastic gradient descent step, right? You can see here that if any number of iterations, you can print here. Yeah, right. Yeah, we can see that now our loss is going down, it's going near to zero. And for in this occasion, we can see that it's our loss is decreasing, so our algorithm, our neural network is improving each time. You can see here the losses for each time, right? So we have trained our first neural network. Let's let's see how it's work with torch.1 with the sample variables. In this occasion are just ones, right? They are not by uniform distribution. Let's see how it works, right? So we can pass our output here from this network that we are already trained, right? See the print of this tensor, right? So it's almost coming to zero. So it's the grad function, as you can see here, the from this output is the adding operation. Let's describe a little bit more, but it's not necessary. Yeah, we can describe, but it's not necessary to describe it. And now let's print the loss for this function. Let's loss NSA. Loss this out and torch that zeros like, right? The same result. So you can see that our loss is almost zero, so it's 1 to the minus 3, right? Let's just instantiate a network, that a new network, let's call new non-trained network, non-trained, right? That it should be an instance from the mynet network, the same, right? And let's print again this value. So for this application, these are all, yeah, we should pass for this O2, let's call O2, and for the non-trained network, we can pass again the same input value, right? In this occasion, this will be O2, and in this case, it should be O2. Let's see how it works. So we can see that if we non-train this network, the loss is bigger, right? And that's because we didn't train properly, just we did a toy example, but there are a lot of ways to do it more properly. So you will see in further class how this should be done, right? This occasion for this toy example, we can see that our train network is working. If we train for more time, it should decrease this value. Right? So there is occasion that we cannot, we don't want to calculate the gradients, like for instance in some inference predictions and just to testing our network. So we can avoid the computation of these gradients with this keyword, with this torch no grads, so which speed up our computation process like by 2 or 3 times normally. So let's see how we can use these no torch no gradients functions. Let's see. We can define it again. This torch dot once. Let's try this one. And by 3, and with torch no gradients for this part. Let's calculate the output value for this train network, right? And let's calculate loss, loss for this part. So let's calculate loss and mean square error. The output should be the torch dot zeros for this part. Okay, let's print a little bit the loss function, this loss value, loss that item, right? And let's describe this tensor. Let's start this tensor. And we can see, right? Oh, because our recommends I what's the couple of things. Oh, what's going on? Yeah, it should be once. Check the net, taking these values, right? Watch that once, right? Ah, okay, yeah, so the same here. Here is like, yeah, sorry about this interruption. So, yeah, in this occasion, we are returning the loss. The loss is this value, so it's really close. Yeah, it's close into 0, and we can see that it's the required grades set to false, and also this not gradient or not gradient are calculated for this operation, for this part of this torch not gradients part, right? So it's really useful in the case of in the evaluation process of the neural network. Perfect. And another thing that we can show is the dot detach of the tensor. This is really useful in the case that we are just training some part of the neural network. For instance, here we can leave the first fully connected layer to behave like it was defined at the beginning, and just train the second part of the neural network, right? So let's define the another class, my net, my not my let's the let's call my detach net, right? Copy all the part that let's reuse our code by copying this part, right? This class. In this occasion, it will be my detach net, will be here the same. And here we can define our first hidden layer to be detached. So in this occasion, it won't calculate the gradients for the first fully connected layer. Okay, and let's instantiate our my detach net plus my print this network like we can see that is the same. It's the same. We have the same structure, the same architecture. Let's print these parameters. It will be the same. It should be the same. My detach network dot parameters for in param. Let's print p. So it's already telling us that it are the same structure. The request grads are set to true. The request grad here in the it's also so it's all similar. So what's happening here? So we had said that for this occasion it was touch or the hidden layer, but we will see how it's work, right? It, right now in the first view we can see that is looks like a similar our non-detached network. Okay, let's train this detached network. So it's my detached network. The loss function will be the same loss function here, and also the optimizer, right? And optimizer, and also for 500 iterations. Oh, so as expected, our loss function is oscillating between some values here. It's not decreasing that we have already seen in the first occasion when we obtain this. This is maybe doesn't use another. In the first moment, we train our network, and let's print a little bit more the loss function that is occasion. We can use this example here just to see how it's work in this occasion, right? Explore a little bit more. In this occasion, we define a torch.once, a tensor phi 3, and we pass for this network. Let's print the loss function between the output and the zeros of the same shape. And in this occasion, we can detach network should be the occasion we instantiate any, because we have trained my detached network. So it will pass the same input. We can pass the same input value and all the same here. And we can see that, well, that's a really big loss for this this detached network. But what's coming on here? Let's describe some tensors like my detached network dot fully connected layers like one, and like the weights, right? This tensor we will pass the same name, so it will be fully connected one, and for the my detached network, right? And let's compare with the first layer. So it will be the net dot fully connected layer, and here is all the non-detached fully connected weights. Here weights. So we can see that all the gradients for the fully connected one is fully connected one detached. So this is a tensor, and you can see that squares grad is set to true, but non-gradients are calculated for this part. So it's like not storing any gradients. So it's like it can update any gradients. So this tensor it remain the same as in the moment that it was initialized, right? And in the non-detached, so we can see that all the gradients, all the values are here, and all the gradients for this tensor are zero. So it's calculating some gradients, and in this occasion are just zero values. We can see the difference here. So it's like a way to just uncouple the neural network by freezing some layers and just training some layers. It's really useful in depending on the application. In other applications like uh, reusing other networks and just training a little bit power from some different applications, transfer learning applications, right? So this is the ending of this lesson. These are the references that are really useful to explore, and this is all for this lecture. I hope you have enjoyed, and thank you for watching.